Hello, everyone. I think we'll make a start. I'm not sure how many are timetabled in this class off the top of my head, but it seems as if we've got quite a few people logged in. So yeah, we'll make a start, and some other people might join us along the way. So, just recapping how we left things last week. I think we were doing some whole wizard stuff towards the end of the session. So we were using the whole wizard feature, talking about the sorts of features that you can create with it, why you would use the whole feature rather than just using a extruded cut or a revolved cut feature. So this week there was going to be a little bit of a sort of conclusion to using the whole wizard feature. But I think what we'll do, rather than just using it in the example that we finished with last week, I've got an example that allows us to have a look at the pattern feature at the same time. So I think we'll have a look at that in this session. I'll just share my screen. Just give me a second. So here we go. But before we get into all that, the actual SolidWorks side of today, I did promise that we'd have a little look at the assignment, which I've managed to put some of the assignment description documents on the shoe site for you. So if you go into Performance Engines, and then there's an assessment section on the left-hand side there. So if you click on that, SolidWorks CAD assignment, the sort of primary document there, the descriptor for the assignment, if you like, is that middle document there. So it's the one that's a Word document. And then that's just in the sort of standard format that you get these descriptors for all your assignments. It's just outlining the percentage of your overall mark that it's responsible for. Word counts there. The fact that Tarsem's the module leader, no doubt you'll have seen these before. There's the hand-in date as well on that. And then if you scroll down a little bit, there's sort of a brief outline of what you're going to be expected to do in the assignment. So I'm not going to go through that word for word in this session. Just know that it's there and you can sort of peruse it, and you can come back with questions related to it and bring them to the sessions. I don't mind that. Probably the most interesting bit of it is the marking scheme, which is the last 2 pages, which is what we're looking at here. So I always say this to all the students that I teach that have this form of sort of project work as part of their assessment. I would attempt to kind of have a copy of the marking scheme at my side or open on the screen as I was actually putting the project together. And then hopefully that will guide you as to what you want to put into each section of your project. So you should be kind of working towards, ideally, sort of descriptions of your project in this column here. So this is the high marks between 100% and 70%. So yeah, if you can keep these phrases in mind as you're putting the thing together, that will sort of stand you in good stead in terms of getting a good mark for the project. Certainly that's how I did it when I was in your position. So yeah, that's your sort of bog standard descriptor for the project. The other 2 documents in there I've put together to try and help you. So we'll have a look at the top one. The top one gives you specifics about what I'm expecting you to do. So if we open that PDF up. So let's tackle this first section here. So the items to be submitted for marking. A report, probably generated using Word. That would be my advice. That's not mandatory. If you don't have access to Word and you're using something, one of the free alternatives like OpenOffice or just using Google Docs, that's fine as well. My preference would be use Word. But submit your final report as a PDF, which you can do easily enough. You can just save your Word document as the final version and save it as a PDF rather than a Word document. That makes things nice and sort of standardized across everyone's work. The next bit, again, isn't specific to this project. This is just general, how you are expected to submit reports properly formatted. So I'm talking about things such as section headings and a contents page and proper referencing. And yeah, hopefully you're aware of all these things already. Again, I'm not going to get into the ins and outs of how to create a proper Word document here. We can tackle that if it really is an issue later on down the line. But properly formatted, and the document should outline your design, optimization, and CAM programming of the parts that you're going to actually design in this project. So those are kind of the broad sections. There's an initial section where you are not yet designing things. You're making yourself familiar with the sorts of products that you're being asked to design. So that's a bit of research first. Then you get into the design sort of phase properly. Once you've come up with some form of initial design, we're going to look at tools within the CAD system to allow you to optimize that design. So we're going to be looking at sort of FEA testing it, looking at the stressors within it, trying to optimize some of the masses of things and that sort of thing. So that'll be the optimization stage. And then when you've kind of settled on what you consider the final design of the parts that you are going to be tasked with, there's a step at the end which involves creating CAM G-code that could theoretically be used to feed to a CNC mill, in this case, and actually machine the parts. So you're not going to be expected to practically do that for obvious reasons. You're not on site. That would be very difficult. But I at least want people to be able to show evidence of having created some CAM programs to actually machine these parts. So yeah, that's the sort of broad structure of the report. As well as that, when you've got your final design, I want you to create obviously the CAM programs to theoretically machine the design from material. But I also want you to create some engineering drawings. So we kind of touched on this last week. We did a real simple little beginning of tackling engineering drawings. We kind of laid out, I think it was a valve that we created as a revolve. So if you haven't used that side of SolidWorks already in the past, we'll be kind of introducing it all the way through the module just to get used to taking our parts through into the drawing creation section of SolidWorks. So yeah, engineering drawings of your parts are expected as part of the submission. So there's a PDF file outlining all your activities with plenty of sort of pictorial evidence that you've completed all these tasks in SolidWorks. And then there's some PDF drawings as well of your parts, which I'll show you some examples of some reasonable ones from years past, just so that you can kind of get an idea of what you're expected to produce. The little note at the bottom says SolidWorks and SolidCAM files can be submitted, but they will not form the basis of your mark. So the reason I put this in every year is a lot of people skimp on the detail in the report, and then in previous years I or other markers have had to dig round in their parts to try and ascertain whether they've done the work or not. So generally, if it's not included in the report, you're not going to get marks for it, even if you've done the work. So it would be not very smart to do that. If you've done the work, in terms of putting the work in SolidWorks, document what you've done. So yeah, that's just a little heads up and warning. They will only be used for verification of the report entries. So in some cases, if you take a screenshot and it's not immediately obvious either a value in the screenshot, the text is too small, we may use them at that point. We may open the SolidWorks files up and just verify that what we're looking at in the report is actually backed up by the actual SolidWorks files themselves. So I'm going to skip over this section that says fixed engine data because I'm going to come back to it. We're going to kind of have a look at the task that I'm going to set you first, and then we'll come back to the engine data. So the task, you're required to model and or design a inverted commas bottom end set of components from an engine, and the details of the engine are above, as we've just spoken about. These should include, so this is not an exhaustive list, but this is the general sort of gist of what I'm expecting from you. These should include a conrod or multiple conrods, seeing as we've got a multiple cylinder engine, pistons, crankshaft, and all associated subcomponents. So again, this isn't an exhaustive list, but rings, so piston rings, various pins holding things together, various bearing types, clips, dowels, bolts, etc. Again, you can flesh that out a little bit more, hopefully, during your research phase of your project. So, on to that. You must research suitable existing designs for these components and produce detailed part models of them using SolidWorks. So I'll read this, and as we come to interesting points, I'll add little bits extra into the description. Your 3D SolidWorks model should detail all aspects of actual working components as closely as possible. Now, I'm willing to accept some sort of simplification of certain components, and the level of simplification will depend on your skill within SolidWorks and the sort of thoroughness of your research that you've done. So yeah, there's a little bit of leeway there. Yeah, you get the idea. This portion of the task is primarily to assess your ability to use SolidWorks modeling techniques correctly. So again, this is giving you a bit of a steer, as in people often tie themselves up trying to marry this task with some of the tasks that Tarsum is working through with you in his lessons. And what I ultimately end up saying is that it would be better to regard them totally separate from each other. I don't mind if you can bring in some of Tarsum's formulas and the sort of hand calculations that you've been doing, but that wouldn't be my preference. My preference is for you to prove that you can research what components exist in this bottom end of the engine. You can model them reasonably successfully, so you're proving to me that you can use SolidWorks to model things in 3D, and then you can perform some amount of optimization on them using SolidWorks again. I'm not testing you for your knowledge of Tarsum's hand calculation skills. So yeah, just a heads up. Will this be in groups of 3? No, it won't. Someone's just asked a very good question. So this is individual work. So every person on this will be submitting their own report. So yeah, it differs in that respect as well from Tarsum's stuff. So onwards, down the document. A working SolidWorks assembly containing all of your components should be produced. Assembly mates should be added to as close as possible. And again, that phrase is sort of repeated from above, as close as possible. Replicate the movement of the components in a real engine. Which again, if that seems not to make sense at the moment, when we get onto assemblies in SolidWorks, hopefully you will begin to understand what's been talked about there. The design of the conrod should be analysed using the simulation tools available inside SolidWorks. So now we're talking about more of the optimization phase of the task. And specifically, we're going to be looking at optimizing the conrod design. So yeah, where was I? Inside SolidWorks. So we're simulating it inside SolidWorks. Simulation data should be used to optimize the design. So this is a little bit of sort of iterative design work where you use some of the simulation tools, you make some design changes based on the results of those simulations, and maybe you run through again and you simulate a second time or maybe a third time and so on. So you make improvements based on evidence, essentially, that you generate through running these simulations within SolidWorks. To be used to optimize the design with the goal of reducing the mass of the conrod through several design iterations, which is kind of what I've just said. Evidence of these optimizations is required in your report. And again, so this is kind of just reiterating that however many iterations you do, it's best practice to document each iteration. How did the design improve through you looking at the results of the simulation and feeding that back in to a design modification. So document each iteration where the design is hopefully being improved on each one. The closeness of these simulations to real-world operation conditions that the components may experience should be discussed in your report. So this is kind of hinting at the fact that you must be aware of the failings of the simulations in terms of you're not 100% simulating the real world condition. So you need to have some sort of comment on that. You need to comment on the differences between actual testing in the real world and the simulation that you're setting up. Will this be in groups of 3? When is this due for? 7th of May. Yes. So that has been sort of pre-decided before I started looking at this. So yeah, back to our Word document here. So there you go. Now I will double check that date with Tarsum. So as I say, I didn't have any input in that handing date, but I'm assuming it's correct. If he's edited this document for this year, then I'm assuming that's set now, the 7th of May. So yeah, but I'll get confirmation from Tarsum for you that that's going to be the handing for it. So anyway, back to where we were. So that's the simulation section. Next section here, we're talking about the engineering drawings. Engineering drawings of your parts and assemblies are required. You will need to research suitable data to include on the drawing sheets, along with suitable dimension and tolerancing methods for your parts. Again, this is sort of marrying up a little bit of part research. What are these parts? What is their function? What do they do? What are current designs? Can I research how this problem's already been solved by other manufacturers or designers? So yeah, it's marrying up what would be suitable to include on your drawings for these specific parts. The drawings should be clear and unambiguous and complete in their description of each part assembly. That's kind of the golden rule for engineering drawings anyway. Unambiguous is kind of the big word there, which is, I would say, whenever you're creating drawings, don't leave anything to interpretation or chance. Be unambiguous in your description of what the part is, what size it should be, what shape it should be, any specific surface finishes that it should have. Don't leave anything up to interpretation as far as you can with a drawing. So yeah, that's the drawing section. The SolidCam section. So we'll be using a plugin for SolidWorks called SolidCam that I'll show you how to plug in. I'll probably, or how to install. I'll give you a link later on when we get to the SolidCam portion of this, and I'll probably produce a little video of how to get it working as well. A SolidCam program must be produced to simulate the machining of your conrod from a billet of material, so that's a block of material. Evidence should be provided in your report that you have experimented with differing machining strategies to reduce overall machine times. So again, this is sort of the way that this activity tends to be done by professionals that use SolidCam or other CAM software. You write an initial program that will remove the material from your block of material and gradually turn it into your part design. And then maybe you'll experiment a little bit with cutting down on the machining time. So you might change the way that you cut some material to a slightly different method and run the simulation again. This is very similar to the way that you might use the simulation tools on your the stressors in your part to optimize the part design itself. This is sort of an iterative process again. You run an initial experiment, you get a overall machining time out of that, you make some modifications that you believe might cut down on the machining time, and then you run the simulation again. And the system will tell you what the overall machining time then is. So again, you may do a few sort of rounds of optimization here and document them all in your report again. My preference is to create multiple saves of the same SolidCAM machining program. So you can have iteration 1, iteration 2, iteration 3, and then you can go back to them and put evidence and screenshots of them in your report and talk about what you changed. Again, a little bit more data on that. Evidence of the availability of tools that you have used in your SolidCAM machining program need to be included. You can't just make up tools and assume that you can buy them out there on the market. So by tools, I mean end mills or chamfering tools or slot drills or traditional twist drills. You can just make them up within SolidCAM. It doesn't stop you. But for the report, you've got to evidence that these tools actually exist. So I've given you sort of a gift there, which is the manufacturer called Sandvik Coromant, which if you search that term on the internet, they have a really nice tool selector that's all online that you can get the data out of, and you can evidence that in your report as well and say, I use this tool, I use this tool, I use this tool, this tool, and here's evidence that they all exist, and I've set them up correctly within SolidCAM. So yeah, and just as a summary of everything that we've talked about above, I would broadly lay out my report in this kind of form. Initially, there's going to be a thought process, planning, research sort of section. Then you're going to get into designing the parts and actually modeling them in SolidWorks. Once you've got those part designs reasonably well established, you're going to assemble them into assemblies. Then you're going to do some simulation and possibly loop back to the part design portion of the activity with that data that you've generated in that simulation stage. So that would be the optimization then. You're taking the simulation output and you're optimizing your part design. Then when you're reasonably happy that you've come up with a final part design, you produce some engineering drawings of it. Again, if you want justification for that in a sort of real world environment, they tend to be used for production purposes or checking. So that's why you want to produce them. And you need to produce the CAM program and document that as well and optimize the length of time taken to machine. Little note at the bottom, the process will not be linear, which is what I keep saying. There's an iterative approach in at least two sections here where you have to take the output of one of these later stages and feed it back in to the earlier stage. So yeah, it's not going to be linear. It's not just going to flow from beginning to end. There's going to be some loop back steps there. You will go back to previous steps as new information comes to light, multiple iterations, yeah. Key function of the assignment is show how a CAD system such as SolidWorks can be used to create a design, including multiple parts that are assembled into an assembly or multiple assemblies, and then to use the system to refine and optimize that design and to test it to a certain degree as well. And then to produce some production data. So in our case, that's going to be engineering drawings and the CNC machining program. So let's go back up to the top, just so that we can finish this document off. So I've given you some fixed engine data there. There is inevitably little questions that crop up from this where people ask valid questions, but that's kind of the unmovable inputs into your design, essentially. These are non-negotiables. It must be a 4-cylinder engine. It must have a cylinder bore of that diameter. It must have a stroke of that diameter. The conrod length, again, I should have edited this. So that's conrod length is measured in center to center. So maybe I'll edit this document and just add that in brackets. Center to center is what conrod length tends to be measured in, and that's the figure. Conrod width, I've actually gone in and bracketed this just to clarify. Across the bearing end faces is 26. You get the idea. So these are the non-negotiables. Everything beyond that is kind of up to you to make a decision on when you've done a bit of research or when you get into actually designing your parts. So that is the only sort of fixed inputs into your design, if you like. Everything else, you get to make the choice. So that's kind of the document. I'm sure as this week sort of progresses to next week and the coming weeks, you'll have questions about it. Yeah, go away, digest it a bit. Bring the questions back to the sessions. I don't mind that. That's fine. And yeah, we'll discuss it as we go through. And hopefully, in the much later sessions, I think we've got 12 weeks of this in total, maybe 11. I'm not entirely sure at this point. But certainly the back end of those weeks, so weeks 10, I would say, onwards, I'll try, as I do when we are on site, I'll try and just open the session up and let people do a little bit of project work, show me what they've done, get my opinion on it, and just have it more like that rather than me just running the tutorial and giving you new information. Because I think by that point we'll have sort of covered all the skills that you need to complete this task, and it would be more useful if you can sort of pick my brains for information that's specific to your project. So yeah, that's the broad outline. There's one more document on there, just because I'm trying to be sort of extra nice to you. This one, a useful guide, annotated marking scheme. So this I put together because I found what I've given you in my sort of outline of the task here can be difficult to kind of marry up with the marking scheme that I showed you in that Word document. The sort of way that things are described here isn't exactly the same as I've described them in my PDF that I've given you. So what I thought I'd do is I'd give you a copy of the marking scheme here, which is this little useful guide, where I've tried to overtype and give you sort of hints as to what this actually means in terms of what do you need to produce for this section, what is going to be expected in each section. So yeah, this is what the little overtype comments are. So demonstrate an understanding of the engineering function concerning the engine component, engine bottom end research and comments. So this is you going away and doing your research and figuring out what these components are, what they do, what current designs exist, why have the current designs been designed as they have, what are the differences between all the different various designs that exist. So yeah, that's that section, your research. Application of engineering principles and FEA to design the engine component. Translation, considered sensible initial design, well modelled, and that's a key section in there. I'm looking for your skill in the ability of using SolidWorks, well modelled, and use of SolidWorks simulation to help improve the design. So yeah, use that. I've produced it to try and help you sort of structure your work that you hand in a little bit sort of more logically. So yeah, those three documents should give you your starting point to sort of make a start on what we're actually going to be hopefully handing in on the handing date. One little extra bit there. So I pulled up some examples of some of projects from past years. So I talked about this a little bit last week. There's a full YouTube video of me. I don't speak on the video because it was kind of answering someone's question that sent me quite a long and wordy question. So I sort of modeled up quickly a similar design to the design that most of the students were coming up with. And then I ran through how to set up what's known as a static assembly simulation. So there's a whole video behind this, and this is just a screenshot from the video. So the link to that video is in the learning materials. If you have a look a little bit lower down the page on the learning materials, there's this video to watch. But that's essentially the assembly or something like that that you're kind of expected to produce. And you can see the conrod there is undergoing some stress testing, essentially. We're applying forces to it indirectly via the piston. You can kind of see the forces applied there with the sort of orange arrows at the top. And we're seeing how the stresses sort of are arranged within that design, and then feeding all that back into maybe refining that design slightly. Where is it under least stress? Do we have to simulate it again? We're obviously simulating it under compression here, but that doesn't complete that testing in terms of trying to test it in a more sort of real world fashion. It will experience other forces that aren't just compressive forces. So yeah, that's the kind of thing that you're sort of looking to produce by the end of the session, at least for your assembly. There's a crankshaft shown there. There's a conrod. The end of the conrod there is actually hidden, but this conrod does have a cap on. It has some bolts. It has a pin holding it to the piston. There's a piston design there. So that's a typical sort of assembly that you would be looking to produce by the end of your project. Few of the engineering drawings. So again, here's a reasonable example of an engineering drawing of the entire assembly. So this is the top level assembly. And this shows kind of, it's got a bill of materials here, which again, we'll cover that skill, creating bills of materials in drawings when we're doing the drawings portion of our tutorial sessions. It's got balloons just sort of highlighting which item number corresponds to which component, and it's got sort of a isometric view there as well, just showing the assembly in sort of assembled form rather than exploded form here. And it's got all the things you'd expect to find on a drawing sheet. It's got sort of a title block there. It's got a border around it. It's got data in the title block. I think we can see it's an A2 sheet. It's at scale 1 to 2. It's got no other sheets in this drawing, so you can produce multiple sheet drawings, but this is just a single sheet. Yeah, you get the idea. Again, that's sort of the final assembly, including all the parts that have been created for this. So I think I've got one more as an example. So that's just a nice one of a little conrod bolt, which seems like quite a boring component, but they're actually quite kind of critical to the whole setup. And they have sort of specific designs. Yeah, for reasons that I'm not going to go into here. I expect you to go off and do a little bit of research on them, and but that gives you an idea of the sorts of drawings that you're going to be producing by the end of it. So yeah, that's kind of outlining most of what I've got for you in terms of the task. Again, do you want to sort of digest all that and return with sort of thought out questions either next week or the week after? I don't want to tie up the entirety of this session just kind of going through the assessment. Is everyone happy to go away and digest that a little bit and come back with some questions that they might have next week? Anyone type yes? Yeah, that sounds okay. That sounds like a plan then, because I'm keen to at least do some tutorial work this week, because we have got stuff to get through. So what are we going to do? Just let me look at my running order. So we've covered the project. Something else, yes, in learning materials, I finally got round to, so learning materials, SolidWorks. I've put a link to the recordings of these sessions on there, so if you click on that, I haven't got week 1 up there yet, but I don't think we did a great deal of advanced stuff on week 1. I think we did a bit of extrusion, so I'll put it up there. But yeah, there's last week, there's the week before, and obviously we're going to record this session, and I'll drop that in there as well. So there's the link to those. That other link that I kind of talked about already, I've just spruced up the link to it a little bit, just made the text a bit bigger. But that's the one to my kind of generic SolidWorks tutorial videos. So again, a lot of the things I've talked about in that brief are included here. There's a whole load of SolidCam stuff. So when we get into SolidCam, there's a lot of support videos that you can watch that I've made specific to what we're going to be doing in SolidCam. And the same with simulation. So you can see there's quite a few on simulation. This design study one's based on simulation. Yeah, that's repeated there. So yeah, you get the idea. There's good stuff in there in terms of what you're going to be asked to do for the project work. So that's that one covered as well. So let's drop in to, I think, the PDF that we have been working from. So in weeks 1 to 4, I think we're in week 4 now. Yes, we are. So yeah, this is the kind of PDF that we've been working from. So if I get that open, I'll shut some of these other things down. Yeah, this is it. And if I scroll back up a bit, you should recognize where we left it the other week. I think we kind of finished off. Oh dear, it's miles up. No, let me scroll back down again. Yes, we did a little bit of that, kind of finished that off, laid out a really rough drawing of that just to get our sort of heads into laying out drawings. Then we did that plate with the whole wizard features on it. Someone's asking a specific question. Just let me read this on the chat. With the small end bearings, are we expected to model all the rollers individually and then make them to the bearing race so that it functions like a proper bearing? That's a good question. No, I wouldn't expect that. It's kind of not the dumb thing when you're producing models such as this. You would put some sort of representation of the bearing in there. What I may show you, and this will be dependent on how fully featured your installation of SolidWorks is there is a library of standard bearings in SolidWorks. So whether you can use that or whether it's not included in the student version, I'm not entirely sure. But as a last ditch sort of way of doing it, other than just modeling up a simple pair of cylinders that just represent the outer surfaces of the bearing, that would be sort of the lowest quality version of representing a bearing. I think you can go to bearing manufacturers' websites such as SKF and actually download the SolidWorks model. So that might be worth a little look. I've done that in previous years. I haven't tried it in a year or so. So I'm assuming they've still got that service. But it might be worth just having a little browse over there to SKF and seeing if you can get the 3D CAD models. Because that would be, the answer to your question would then be yes, but you don't have to model them up. You can just import them from SKF. And at least then you should know that they're going to be accurate to what's available. Because obviously SKF are the bearing manufacturer. So yeah, that's a little bit more detail, but as a last ditch sort of way of doing it, just a cylinder representing the internal surface that mates on the shaft, and then a cylinder representing the external surface that mates against a bore. That would probably be good enough. So that's that question, hopefully. But I'm sure we'll come back to questions like that in the coming weeks. So yeah, we did a little bit of work on a simple plate like this. We put some whole wizard features in the corners, I think. We talked about the fact that you can do counterbore holes, countersinks. You can do threaded holes, which we didn't actually do, but we are going to do this week in a different example lower down. So you can see, hopefully, at the end of this tutorial that I've sort of outlined here, there is a representation of a threaded hole there, which, as I say, we're not going to do it on that plate. We're going to fold it into another little tutorial that we're going to do on patterns. So that's what we're going to tackle first. So if I scroll down a bit, so you can see some of these examples, I talked about them and said you're free to go away and try and model these up. It's just practice, basically. So this one practices revolve features, extrude features. There's a little bit on there which is chamfered, I think. Yeah. Yeah, there's a chamfer on the end there. There's some Hole Wizard feature stuff down here as well. But we're not going to have the time to run through every single one of these examples in the sessions. They're just there. I've even given you a screenshot there to show you how I actually tackled that part model. This is where we're going to start this week. So patterns, there's not a great deal of data there, but what I'm going to do is I'm going to model this block up and you can follow me. So what we're looking at there is just a little test block that I've created in SolidWorks. And the only reason I've created it is so that I can illustrate what the different pattern types do within SolidWorks. There's lots of different subtypes within the patterning tool. So the patterning tool takes an original feature, doesn't have to be a hole, it doesn't have to be a boss. These just all happen to be either holes or bosses. And it creates copies of it. And it can create copies in a regular fashion, like this pattern here. That one's known as a linear pattern. It can create copies around a center axis. So you can imagine a center axis there. That was the original. And then it just rotates the copies around the center axis. That's a circular pattern. We've got a fill pattern on the side, which is, I've used it to create these bosses that stick out. But that's quite a good one if you want to use it to create perforations in thin sheet metal parts. So if you've got a thin sheet metal part that you have to put perforations in, either for a fan or some sort of ducting or something, that's a good one. You do an extruded cut and then you pattern it across the entire face of one of the pieces of sheet metal. So that's a fill pattern. It just fills an entire face with copies. So if the face gets bigger, the number of copies increases. So that's quite useful, quite labour saving, because otherwise you have to set it up as a linear pattern and control it with specific dimensions, which you then have to edit if the face gets bigger. Path pattern, so you can sort of see that on the side here. I've left the sketch visible and coloured it in this sort of pink colour so that you can see what the sketch, what shape it is. And you can see I've just done almost a freehand shape there, and the pattern follows it. So that can be quite useful in certain situations. And then there's one on the back of this block, which you can't see, but I've got the block open in SolidWorks, if we can have a look at it. So on the back of the block there, if I just rotate around, there are a number of holes. So this is called a sketch pattern, and you can basically drop copies wherever you put a little dot in your sketch. So this kind of works a little bit like the Hole Wizard feature that we were using, except you don't just have to apply it to holes, you can apply it to any feature that you want. You can just drop a copy wherever you put a dot in your sketch that's controlling it. So yeah, we'll have a quick look at that. I'll guide you through just creating it, because obviously there's not enough info there for you to create it to the dimensions that I have. So if I back up my creation of this thing, so it started out just as an extruded boss base feature, and the sketch for that extruded boss base was on the top plane. So if you want to get a new part initiated, tell the system that you're going to create an extruded boss base. So we know how to do that by now. Extruded boss base, it'll ask you what plane you want to sketch on. You want to sketch on the top plane, and then the sketch is simply, so I'll drop into this sketch and sort of do each piece with you. So it's a 500 by 400 block. So let me recreate that. So I'm deleting my copy of it. And then I'm getting the center rectangle tool, locking the center of the rectangle to the origin, dragging it out, dropping it, getting the smart dimension tool, and then I said 500 by 400. Like that. So really simple. And then OK the sketch. So you should drop into the creation of the extruded boss base then, which should look something like this, like that. And the depth that we're going to have is 60 mil for that, so 60 millimeters in what I'd consider as kind of the upward direction. So you can see the plane is down at the bottom of the block of material there. It's not that critical getting it exactly as mine is, but yeah, it would be useful. Then we can OK the feature. So we've got our extruded block there. Then I think I put quite a large fillet on this front right edge there. So that would be the fillet feature. Fillet feature's decided not to work. So I'll have to reinstate it. So what you want to do is just click on the edge, and of the icons that pop up, the fillet icon is one of those icons. And then that fillet feature, I've made it quite large. It's 130 millimeters. So it just puts a nice little round. And the reason I'm doing that is when we do the circular pattern, one of the methods of telling the circular pattern where the center point of your pattern is you can click on a cylinder. So I'm now creating a quarter of a cylinder there. That's why I'm putting that fillet feature in. So I've got a cylindrical face to select so that when I create that circular pattern, it knows what curve to pattern the pattern members around. So insert that fillet on that edge. Then we're going to get the hole wizard feature. And I'm just going to put a hole over here. So I'll recreate that as well. So you would go hole wizard, and then what you would be looking at is this menu. So you'd be looking at the type menu. So in our case, we're going to select a countersunk hole. So it's that icon in the middle of the top row of icons on hole type. So select that. The standard that I'm choosing is to use BSI as my standard. The type of fixing, so that's what that means. The type of fixing that you're expecting to drop into this hole. So in this case, it's a hex socket head countersunk. So that would use an Allen key to turn it essentially. So that's what it's intended for. So hex socket countersunk head, that bottom one on the list. The diameter of it, or the standard that it's going to adhere to, an M8 size fixing. So M8 fit we can leave on normal. I don't want a particularly sort of baggy drilled hole or a particularly tight drilled hole, so the fit just normal. End condition through all in this case is fine. And then everything else you can see, I haven't got anything else ticked. Nothing else is selected here. So that's the setup of that hole. Then on position, so you want to click on the positions tab. You will obviously click on this top face to tell the system that that's where you want to drop your holes onto, the top face of the block itself. And then you just want to initially just click to drop the hole, then hit escape. So you're not going to drop a second hole. And then just dimension it like I've done there. 200 from the center plane and 20 mil upwards. So I might delete those and put them back in so that you can see me doing that. So 220. So Smart Dimension tool, click on that vertical plane there, click on your point. Mine's already 200, but at that point you just enter what you wanted yours to be. So 200, and then it was dimensioned upwards from this sort of front edge of our part to the hole center again. And again, mine's already on 20, but yours obviously won't be. So you'll just enter what you want that to be as well. And then that second one that I've dropped, I obviously don't need that. So I'd get out the Smart Dimension tool and just delete any points that I don't require. So that's it. That's the whole all spec. Click on OK, which was the green tick at the top right there. And that should be our whole feature. And again, because we're using the hole wizard, it knows it's given it a correct name. If we'd just done this with a revolved cut, which we could have done, yeah, hopefully you can see how you would create that with a revolved cut. You'd sketch the half section of the hole. So we talked about the half section versus the full cross section shape. So you would sketch that half section, and then you would just rotate it around a center axis and it would cut that shape out. But far better to use the hole wizard feature. And in actual fact, that's exactly what the hole wizard feature is doing in the background for us. So you can see there I've highlighted one of the sketches that the hole wizard feature has created, and you can see it is actually the half section of the hole. So that's all the hole wizard feature does. It does the cut revolve automatically for you, and you get all this extra information. So it's named the hole properly. It knows that it's for a countersink fixing, so it's put CSK at the start for countersink. It knows that it's intended for an M8 sized fixing, so it's put that in there. It knows that the fixing that we selected was a hex socket head type, so it put all that in as well. And when we come to produce drawings of it, we can pull that information plus extra information through into the drawing without having to re-enter it. So yeah, hole wizard feature is by far the best way of creating holes. You kind of have to have a really good reason to not do it that way. And there are certain scenarios where you wouldn't use the hole wizard, but 9 times out of 10 or more, you would use the hole wizard feature. So what are we going to create next? Our first pattern, I believe. Oh no, all my patterns have stopped working. So let me see if I can fix this. I've been playing around with this, so mine's not working anymore. It's because I deleted that initial sketch and then recreated it, and the system has a problem with that. So let me temporarily shut this copy down, and I'll bring it in again off the hard disk, and then it should work. Pattern block, there it is. So that's the danger. I mean, that's sort of a good word of warning. I'm sure I've talked about this a little bit when we were talking about is it wiser to attach your sketches to the base planes, or is it wiser to attach them to a face of your model? And as I was saying, my overriding advice is if it's possible to attach them to the base planes and not suffer any ill effects because you're doing that, then I would always choose the base planes. And that's because any changes to your model have the potential to ruin other features. And you saw a good example of it there. I played around in that initial sketch to such an extent that the system didn't understand that the new rectangle shape that I created wasn't the same rectangle. It saw it as an entirely new shape. It didn't realize that I'd just replaced old for new and they were identical. It doesn't work like that. So the fact that I deleted all this sketch initially to show you how to create it meant that the rest of my part failed there. So yeah, that's sort of a word of warning. That changes that you make up here affect everything else down below. But anyway, where are we? We're just about to create our first pattern. And our first pattern is going to be that. So we're going to use the linear pattern. So I will do as you're doing. So you've got the hole there. There's various patterns on the features toolbar at the top. You can see that there are various ones because it's got a drop-down arrow below the actual one for linear. And you can see all the other different types in there. But for this particular hole, we're just going to use the linear pattern. So you can just click on the linear. And then direction 1, I should have probably taken note of what the spacing was, but we'll make up the spacing. It doesn't really matter. So what am I going to do? What it's asking for, and you can tell it's asking for some input because this box is highlighted in blue, which we've said before many times that when the system does that with any of these sort of entry boxes, it's waiting for some sort of input from you, the user. And it's usually waiting for you to click on something on the model itself. So for a bit more information, you can hover over the box. If I can get mine working, here we go. And it wants a direction reference. That's not that descriptive. It gives us a bit of information. But if you want even more information, you look down at the bottom left there. And it says, select an edge or axis for direction reference. Select a face of a feature for pattern features. So the thing that we can draw from that is, one of the things it said is an edge is an acceptable reference. So you can see there's an edge on the block at the top there, and I'm going to click on that. And then direction 2, it's highlighted now. Initially, I'm not going to pick a second direction. If we have a look at our reference, you hopefully can tell there are rows of the pattern here, but there are also, there are columns and there are rows. Now, with linear patterns, you don't have to create a sort of grid work like this. You don't have to have the columns. You can just use it to pattern in a direction, which is what we're going to do initially. So that direction 2 that it's asking for some input in, I'm just going to ignore. I'm not going to give it a second direction, just to illustrate that you don't have to. The thing that I'm going to do is I'm going to tell it what feature I want to pattern. So you can see hopefully down below, there's a box that isn't glowing currently that says features and faces. So I'm going to click in there, and then all I have to do is click on some face or edge that is part of the feature that I want to pattern. So you can see all the faces of this hole. When I hover over them, I get a little tooltip, if I can make it work again. There you go. Telling me what the feature is that I'm hovering over. So that's a little check just before you click and you commit to selecting one of these faces. It's worth just letting that pop up and just say, yep, it's definitely the hole that I'm clicking on. Because if I clicked on the block itself, that's a different feature. Obviously, you can see there it said Boss Extrude. So yeah, click on the hole, then I get a preview of what the current pattern settings are going to look like. And you can see these are too close together. So we want to increase the spacing between the pattern members. And helpfully, it's put a little sort of floating entry box there that gives me the two main controlling numbers, if you like, that are driving this pattern. They're also available on the left there, but why bother moving your mouse all the way over there when you can just edit them in this box that it's provided? So spacing, let's bump the spacing up so that they're separated by a little bit of material, so 30mm seems acceptable. Instances, so a little heads up as to what that means. You might assume it means number of copies, but it doesn't mean number of copies. It means number of total holes, including the original hole. So if you count them there on the preview, there's 5 copies, but it counts the original as one of the instances. So don't make that mistake. That's a sort of comment. It seems logical just to think it would be the number of copies, but it's not. But yeah, you're not the first person to think that if you would think it's the number of copies, but it isn't. So let's just to prove that we can edit that, let's turn it down to 5. So rather than type in 5, you can just use the little up and down arrows there. Let's say we're happy with that. Then we can click on the green tick. I had to click twice there to get out of it. And we've got our pattern of holes. But we're not happy with that. We want some rows. So we've created columns there, essentially, if we're looking at it in that orientation. So we've created the columns, but now we want some copies in rows. So let's get back into that pattern feature, which hopefully we know how to do now. Any feature, you just click on it in the feature manager, and then that first icon that pops up at the top left of the icons that appear is edit feature, and that takes us back into the kind of setup dialog of the feature that we need to edit. So what are we going to do? We're going to give it another direction reference. So you can see it's hidden that direction too because we didn't put anything in there. So it's just closed that little bit of the menu down. But we can open it again. Again, as I always say, if there's a little down arrow or a side arrow at the side of an option, it means there's hidden options within it. So I've opened that up again. I've already said I want to give it a direction for its direction number 2, so I'm going to click in that entry box. And then this time, rather than picking an edge like we did the first time, I'm going to pick that plane there. And what it interprets when I do that is that I mean normal to the plane. So again, it may seem logical that you would think, well, that plane runs left to right, so aren't you just selecting the same direction reference as that top edge? And logically, I agree, that might be a sort of logical interpretation, but that isn't how it interprets it. It interprets it as meaning normal to the plane. So that's at 90 degrees to the plane. Now we're not seeing any new rows in our pattern, and that's because the spacing and the number of instances for the second direction, you're able to set them independent of the spacing and the number of instances of the first direction. So you can see here, we've got a little pop-up saying direction 2, spacing 10 mil, but instances 1. So we've already said it classes the original as instance number 1, and then it starts counting 2, 3, 4, 5 from there. So we need to bump this up a little bit as well. So let's go up to 3, and you can see now we've got 2 copies, or 3 in total, including that original row that we created at the top. So the spacing is still a bit tight for this whole feature. So let's bump this spacing up to 20 millimeters and see if that solves it. Yeah, so there's enough material there that they're not sort of overlapping each other. So yeah, that's your linear pattern essentially. So we've covered all the major points there. You can have it in 2 directions, but you don't have to. You can independently set the row spacing and instances to the column spacing and instances. I suppose the only thing that we haven't really covered there is don't assume that the rows and the columns have to be at 90 degrees to each other. I've just selected that in this example just for simplicity as much as anything. So in one direction it goes off in this direction, which is actually the X axis in our world, and then in this direction it goes off on the Z axis, but it doesn't have to. If you've got a sloping edge that you want to choose that cuts across the part at a sort of weird angle, you can select that as well. So don't assume they both have to be at 90 degrees to each other. They don't. So if you want to OK that, just click on the green tick and you'll get your pattern feature. I think I'll tick on it initially, but then I'm going to delete it because you can see I've still got my original. So I've already created this feature. I was just doing that just to show you the actual steps involved. So there's my feature. Mine's slightly different. I think the spacing's slightly different to yours, but it doesn't matter for this example. So let's go on to the next pattern type. So I'll fast forward 2 features here. So you can see I'm using the, I can never remember the name of it. I think it's the modeling bar. So this blue bar here, which I'm sure we covered the other week, allows me to kind of go back in time to before I modeled something and make it temporarily become suppressed. So it temporarily disappears. But you can see it's just grayed out in my feature manager. So where I'm looking at the modeling process is where that blue bar is. So what I can do is just temporarily let those 2 features recreate themselves just so that I can see what they're doing. And you can see there, hopefully, there's a extruded boss initially, which is that feature there. So it's just a hexagon shape, which I'll show you how to create in a second. Those are the dimensions of it, which I might just take a little copy of so that I can have that off screen as a reference. So I'll take a little quick snip of that, use that as a reference, and we'll create that ourselves. And then the circular pattern feature gets used with that curve as a reference direction, if you like, or that supplies the center axis of our pattern. So I can show you the center axis if I can get it visible. Maybe I can't. That's strange. That is odd. It's not showing center axes for some reason. But anyway, we don't need to see it to know that we can use it for a circular pattern. And then there's a circular pattern being created. And the circular pattern has 9 pattern members. You can see it there. And it swings through a total angle of 200 degrees. So those are the sort of 3 inputs that we've had to give it, or 4 inputs. We've given it a kind of cylindrical reference face as a direction. We've given it a feature, which was this hexagonal boss. We've told it what total angle it needs to go through, and we've given it a number of pattern members, which is 9 in this case. So those are the setup steps. So let's create that together. So I've gone back to before I actually created that. It's an extruded boss again. So click on extruded boss. It's asking us which face we want to sketch on. It's going to be the top face of our main block. This time we're going to use the polygon tool, which kind of lets you create any equally sided regular shape. So a polygon, basically, if you know the term. So click on polygon. How many sides do we want? We want 6 sides on our shape, but you can see you can modify that. So you can use it to create any polygon. All the other settings I think we'll leave as standard. And then the first click places the center point. And then I'm purposely not going to let this lock itself onto horizontal, because I want to practice manually putting our relations in to hold it in place. So I'm going to drop it about there, like that, on sort of a odd angle. And then what I want to do, at least initially, is I want to exit the polygon tool. So I'm going to press escape. And then I want to go in and lock one of the edges. So let's say that edge. So I'm going to click on the edge and lock it to horizontal. So it's just practicing being able to do that ourselves manually, rather than relying on the sketch sort of setup to help us lock it in position. It's just making sure that we can do it ourselves as well. Then what I'm going to do, I'm going to put some dimensions on this. So I'm going to get the Smart Dimension tool. I'm going to dimension the flat to flat as 20, like that. And then I'm going to reference that outer edge of the actual part to that point there, and set that as 20 as well, like that. And then maybe I will just want to investigate, how is it still free to move? So I'm going to press escape to get out of the Smart Dimension tool and just try and drag this out of position now, just to get a sense of what is its degree of freedom. How is it still free to move? Why is it still coloured in blue is the question that we're trying to ask, which hopefully is obvious. We've not locked its vertical position yet. So again, just using my little screen snip that I took before, you can see that it's 40 mil up from some kind of significant point down here. So that point is where that curve meets that vertical edge. So you can see there's a point that pops up there when I hover over that sort of transition between the curve and the edge. So I'm going to get my Smart Dimension tool back. I'm going to zoom in a bit and click on the bottom horizontal of my polygon, and then go down till I find that point, which is there, and then place my dimension and tell the system that it is 14 mil up from there, like that. So that's what we should have. And again, it's worth checking if it's fully defined. Yeah, it says it's fully defined at the bottom. It shaded it in, so we're happy. So click to OK the sketch. Then we give it a depth, which in this case happens to be 20 millimeters as well. So I'm just going to drag it up to 20 there. And then you can kind of see there's a little icon that looks like a mouse with a green tick on the right mouse button. So that's a way of shortcutting to OK a feature. So it's basically saying if you're happy with this feature as it is, click on the right mouse button and I'll interpret that as you OKing the feature. So I'm going to do that because, again, it's worth learning these little tips because they speed up your modeling process. So rather than moving all the way over here and clicking the tick, I can just hit the right mouse button. So let's create that pattern. And I've already said it's a circular pattern, so you access it in the drop down below the linear pattern that we've already used. So circular pattern, it's the next one down. Direction 1. So it's asking for an axis, and I'm going to sort of disregard that and not pick an axis, just to illustrate that you can pick axes as the reference point. That's perfectly valid. But you can also pick things which themselves have a center. And a piece of a cylinder, which is what this face is, this big fillet face, has a center point, clearly, because it's just a radius. So it was created, if you want to think about it like this, from a quarter circle that was sketched and then cut away from that edge or that corner. So it obviously has a center point because it's a portion of a circle. So there's a center axis in there, even though we can't see it. And the system is happy to accept any cylindrical face as a reference for a circular pattern. So we're just going to click on that face there, and it accepts it. So even though it says pattern axis, you don't specifically have to stick to just clicking on axes. You can select cylindrical objects as well, and it will accept them. So we're getting a preview of the current settings, and let's have a little look at what it's doing over here on the left. So it's creating a number of copies. So it's creating 3 copies to equal 4 instances in total, including the original, obviously. And it's equally spacing them, and it's traveling through a full rotation, so 360 degrees. So we can edit any of these things. In our example, we had a run of these copies running around here, and they stopped at 200 degrees. So that's the first thing I'm going to change. I'm going to change it from 360 to 200, like that. And then they appeared to all be equally spaced, sort of one copy to the next copy. They appeared to be equal, so I'm going to leave it on equal spacing because we're describing this pattern in terms of its total angle travelled. We've just input that, 200. The other way to define it is the angle between each copy. You can do it that way as well. But for this example, equal spacing and 200 for the total angle. And then I think the number of copies was 9. So we just tap 9 in there. Sorry, the number of instances was 9. I've even started doing it now. It's an easy one just to slip into. So number of instances is 9. The preview looks good. So at that point, you can OK the feature. And you should see that feature. I'll do it, but then I'm going to delete what I've just done because I already have a copy of that. So you can see my suppressed copies there that I had before we began this. Therefore, I don't need those 2 copies that I've just created, whereas you will, because you're just creating this block. I've got an orphan sketch there that I don't need as well, so let's delete that. Again, you won't have to do this step because you're creating these from nothing, from afresh. So next pattern type, let's have a look. So I'll temporarily unsuppress it. So it's these ones on the front. I'm just going to switch the axis display off because it seems as if the axes have become visible on my system. I think I switched them on and forgot to switch them off. So yeah. Again, this isn't the best example. A real good example would be a mesh. So an extruded cut through an existing object creates that kind of mesh shape. But we'll learn how to use the feature even though we're using it to pattern a boss. So first things first, what is the spec of the boss? that's the spec of it. So I'm just gonna, in fact, I think we might create this as an extruded cut because on reflection, I'd prefer an extruded cut. So that's the spec of that. So let's temporarily suppress these and create an extruded cut. So you can see that there, extruded cut. We're sketching on this front face, which we kind of already said. And then I'm just going to kind of make this up on the fly. So let's use that center point slot as our sketching shape again. So center point slot. Let's place the center about there. Let the line lock itself to horizontal. So when you see the horizontal icon appear, even if the line doesn't quite look horizontal, you can just click and it will lock itself to horizontal like that. Then we'll drop the width of the slot as well, and then start dimensioning using the Smart Dimension tool. So let's give it a height. I'll zoom out a little bit just to see the scale of this a little bit better. Let's make it 8 mil. Sounds reasonable. And then I'm going to give it a distance in from the edge here. So I'm going to select that edge and that center point there. And 10 mil seems reasonable, so we'll change that one to 10. And then I'm going to pick the edge of the slot itself and the top edge, and we'll maybe make this one a little bit less. So let's see what this looks like at 5. Yeah, that seems reasonable. And then we just got the length of the slot, because you can see this edge over here is still blue, so we need to add a distance of the width of the slot itself. Let's go for something around 18, maybe a little bit less. Maybe 15 might be, yeah, 15 looks okay for these purposes. We may come back in and change that. We'll have a little play around with it and see how it looks. So, are we going to send these through the whole part? I don't think we will. We'll give them a depth. So let's exit the sketch. That's the first thing. So we'll OK and exit the sketch. And then I'd probably want to rotate my view around a little bit so I get a little bit of a better view of this. How deep is it at the moment? Let's send it 50 mil into the block like that. Yeah, so that's fine for our purposes. So what we're going to do, I said in the kind of intro here, is in this pattern type, which is going to be the fill pattern, you essentially, like all patterns, you have to tell it what feature you want to make patterned copies of. So we're going to tell it this cut extrude. But the other input that it requires is what face of the model do you want to fill with copies of that feature. So what we're going to do is we're going to select that face there. And then the various methods that it arranges the copies, you can then tweak and you can play with. So it can copy them in a sort of honeycomb style. So I think if you set the copy angle at 60 degrees from each copy, you get copies that arrange themselves in that sort of stacked hexagonal style. And there's various other types, but let's get it up and running. So I've just made sure I've not got anything pre-selected. So you can see I had that face selected, it was highlighted in blue, and then to deselect I'm just clicking in some empty space over here. So make sure you've got nothing selected. Then in the pattern drop down, fill pattern is what we're going to use. And then the first bit of input is, so this is the fill boundary, which in our case is a face on the model. But it needn't be. You can create a sketch and you can sketch a perimeter that it will accept that as well. But in our case, it's just this face that our slot cut feature happens to be on. And then again, we have to manually select another entry box here. And just like the other features, or the other pattern features, there's an option kind of a little bit down the dialog there that says features and faces. So we're going to select this one. That's the one if you're picking a feature, which we're picking an extruded cut. So that is a feature, but you can also apply it to faces of the model as well. So feature is what we want, feature. And then we've got to click on something which is part of our extruded cut. So any of those internal faces in there would suffice. And as you hover over them, you get that little tooltip that pops up that just confirms that you are going to select the correct feature if you click on them. So you're looking for extruded cut, which is there. So click. Then we get a preview of what the current settings are going to do. So you can see that if we look at it sort of end on, normal to the face. And then let's have a little play around with some of these settings. So what's the top one? Instant spacing. So this is the general center to center distance between the copies that are produced, certainly on this top line. So if we just roll that up and down, we can kind of see what it's doing. So the increments that it's rolling by default, when I click these up and down arrows, is 10 mil. So it's jumping 10 mil each time. Now that's not that helpful. We can set that to a slightly smaller increment, but not while we're in this dialog itself. So yeah, hopefully you can see the kind of effect that that's having. Let's set that to something around about 30, seems reasonable. So that is both affecting the center distance here, but it's also in combination with this 60-degree setting here, creating this copy way down on the next row down. So let's have a play with the angular measurement, sort of get a sense of what's happening there. So if you imagine there's a center point in the middle of each of these slots, and there's a line that you can trace from that center point down to the center point of this slot, we're changing the angle of that line. So we're reducing it slightly now. So as we go down, you can see that that angle's getting shallower and shallower and shallower, and then we get another row of copies coming up, and so on and so forth. And let's make something that could conceivably be used to create some mesh work. Yeah, 30 and 16 is getting pretty close to what I'd consider looking like some sort of meshed metal, thin piece of metal. The other options on there which aren't as critical. So there's an option which tells the system to avoid putting copies too near the boundary of the edge. So if you're worried that, let's say, your thin metal sheet is getting too weak around the boundaries, you can put in a margin, just like you put in on a Word document. So it will tell it to avoid things which are too close to the margins. So I'm just going to bump this value up. There you go. So if we put, let's say, 8 millimeters in there, it wipes out the copies that were near to the margins. It's also got the one over here. So I think there was another copy there. And because that was too close to that margin, it's got rid of that one as well. And then you can give it a direction reference. So currently, it's kind of copying in what I would consider a horizontal, and then it's taking its angle reference relative to that. But what we can do is click here, pattern direction. Currently it's picking that long bottom edge. If we switch it to this vertical edge, yeah, we ruin the pattern entirely. And that's because the 16 degrees now is referencing a different edge. So we would have to play with that and get it set up again if we can. Yeah, there we go. So we're getting a similar thing happening there that we were getting before. So yeah, you get the idea. You can play with that for a long, long time, but it is particularly, I have actually created laser cut meshwork stainless steel parts using that. So that's what it can be quite useful for. And used in combination with a hexagonal sketch cut or an hexagonal extruded cut, and with the right angular spacing, you can create missing hexagonal shapes, and you can create sort of quite a nice grid work, quite a nice mesh work. But yeah, you have to kind of get a sense of what the settings are doing first. So there is a certain amount of play that you have to do in there to get the sense of what's actually going on. And there are different pattern layouts. So we were doing the one that's known as a perforation. There's a circular one as well, which you can't really see on this face because our original pattern member is right up in one corner. If we had a huge square face here and we put our original in the center, then the circular would make a lot more sense. But in this instance, it's not that obvious. So yeah, we're not going to play with all the options in there, but know that it can be useful in certain situations. So anyway, what were we going to leave it set on? I think we're on about 17 degrees there. Yeah. So if you set everything back to that, that's a reasonable way to leave it. So 30 millimeters, 17 degrees, 0 on the margin, and the edge that you want selected was that original bottom edge rather than the vertical one that we selected. And then when you get all the settings like that, you can OK the pattern. And that's the sort of thing that you end up with. So that's that one. I'm going to keep that cut in preference to my Boss version that I had when we came in. So my Boss version then gets an error. You can see, again, this is good that we're coming across these errors in the tutorials because I can sort of give you a heads up that this is a situation that you can get yourself in SolidWorks, and it looks like it's sort of broken, and it is, but you can always go back and fix things. It's not a big sort of emergency. So it's basically saying the place where you drew your original sketch when you had a Boss Extrude feature on here kind of is missing. So you can see that. That face, as it was, no longer exists. It's been replaced by a new face that has all pieces missing all over it. So it's unwilling to allow that sketch to create my original Boss Extrude feature. So that's why I'm seeing these little red X's on mine. And in this instance, all I'm going to do is delete them. But what I could do at that point is choose to redefine them in some way. But yeah, just know that they're there, and at some point you'll make a change in a model and the system will call you into question about it, and you'll have to try and fix that change that you've made in some way. So next pattern type, let's have a look what we're gonna create next. So this is the, if I get the right terminology, curve driven pattern. So you can see these are the two sort of starting entities that we need to create this pattern. We need a feature 2 pattern. So in this case, again, I've just created a simple little boss that sticks out the side of the block here. And we need a curve, which is generally provided with a sketch. It doesn't have to be. We'll see later on in some of the much later tutorials, you can use equations, or you can use the output of a simulation to create a curve. But in this case, I've just created a sketch, just a freehand sketch essentially. So what we're going to do is we're going to copy this feature along that line. So it's a curve driven pattern, and it's going to look something like that. So all you do is, as I say, you give it the input of the feature that you want to pattern, the curve that you want to pattern along, and then I believe it's just an instance count. So it's a total number of instances. Now we can double check that just by seeing the number that's driving it. So there's the number. It's hard to spot, but it says 26 there. So yeah, that's been driven just by the total number of instances along its length. So let's set that one up as well. So again, I'm going to temporarily suppress my parts. So for this one, the curve's got to be, well, no, let's create the boss first. We'll create the boss before the curve. So it's an extruded boss base. We should be getting good at these now. We're going to sketch on that right-hand face. I'm going to create it as, let's create it as a triangle, just to be different. So I'm going to use the polygon tool. I'm going to roll the number of sides down to 3, which is a triangle, obviously. I'm going to click to place the center and then drag it like that. Hit escape because I don't want to create any more. Put some dimensions on it just to position it. relative to the edges of the block. So 7 upwards, and then let's say around about 12 in from the side like that. And then we have to size the actual triangle itself, so I think I'll do a length along one of the flat edges, and we'll have that as 10 mil, like that. So that's fine. Don't worry if you haven't got these exact measurements. It's just an example of how you use the pattern. So I'll exit the sketch, create my extrude. That looks a little bit too deep for our purposes, so I'll just scale it back a little bit. Should we have it at 10? Yeah, 10's fine. So that was 10 on the extrude. So that's our initial extrude. Now what I'm going to do, I'm going to create just a sketch which isn't going to be part of another feature at this point. It's just a sketch on its own, which I don't think that we've done yet. So if you just want to initiate the creation of a sketch and you don't want to instantly use it to create a feature, the way that you would do that is select the sketching tab and then just click on sketch on the far left hand side there. And it asks us the same question as we get asked when we are creating these extruded features. It says, where do you want to place the sketch? So on this side face here. And we're just going to sketch something freehand on here. So the specific sketch tool that I used to create that kind of wavy line that I had in the example was the spline tool. So there's an icon there that looks like a little bit like a wavy line. And it's good for creating these sorts of free-flowing splines, is the technical term for them. Now, they can be a little bit hard to control their shape. And in this instance, I think we're going to leave the spline totally underdefined just for this example. But we probably have a little play with it, just to give you a sense of what you can sketch using this tool. So get the spline tool. And what I'm going to do first is I'm going to make some reference to the position of this extrude. Because I know that I'm going to pattern this extrude, I'd like my swirly shape to begin somewhere within the boundary of that extrude itself. So I think I'm probably going to start it there. So the center point of that face seems like a reasonable point to start my spline. So when I can see the center point visible there, I'm going to click. And then all I'm going to do is I'm going to alternately go up towards the top edge, not on the edge, but near it, sort of there. Click, and then go down towards the bottom edge, somewhere about there, and click. And then back up towards the top edge, maybe about there, and click. And then one last one somewhere over here. And then click again. And then I'm going to hit escape. So there's my spline. One big problem, it goes beyond the outside of the edge there, so I'm going to have to correct that. So let's have a little play around with that. So let's just drag some of the points that I dropped. So you can click on a point and drag it, and you can see the sort of effect that that has. So in terms of technically what is a spline, it's a sort of constantly varying radius of curvature. So no part of this spline is a portion of a circle. So it's not a traditional arc. Its radius curvature constantly changes along its length. And what rules does it follow? It hits these spline points that you drop in space. So wherever you drop one of those, it's going to pass through that point along its length. And you can see the kind of effect that I'm having by dragging these things around. So it's good if you need to create sort of free-flowing forms. There's more advanced control over it. You can see when I click on a point, I get these drag handles. And there's one here that if I click and hold, I can vary the effect that this point is having on the angle of the spline. So you can see that happening. So that's that one. And then if I click on just the arrow there, not the point on the end, just the arrowhead, and then drag backwards and forwards, hopefully you can see the effect that that's having. It's varying the sort of influence that this point is having on the rest of the spline. So when I drag this handle out, the angle that I've set for this point is having more effect further along the actual spline. And then if I drag it back, you get sort of a pinch effect where this angle is having just a tiny little effect here, and this angle down here is taking over, so it's creating a kink down here. So yeah, we're not going to get any more than that into splines, I think, but know that they're there. You've had a little sort of intro as to what you can achieve with them. It's nice if you create them to relate it to automotive. If you're creating things like body panels, it's perfect for that, or aerofoils and things like that, where gas has to flow over it in a sort of smooth manner. This is the perfect tool for doing that sort of thing. So yeah, but we're just using it to create a pretty pattern along a line. So as I've already said, I'm not going to put any dimensions on that, but just know that I could, and if I was using it in a real project, it would probably be wise to lock down the positions at the very least of these points, which you could do. You could do a vertical dimension down from an edge and then a horizontal dimension. So just lock the points in place. But we're not going to do that for this example. We're just going to click on OK. And then another skill from the block that we were looking at when we came in, which is useful to know how to do, but it's not specific to patterning things, is when you've got sketches in a part and you've got multiple sketches. So let me make all of mine now visible, if I can do that quickly. So there's a sketch, and there's another sketch, and there's another sketch, and there's another one, and then there's loads more down below these. So you can see the part by default is coloured sort of a grey-blue, and the sketches by default are coloured in grey. Not terribly easy to see or pick them out, one sketch over another. It can be really useful to make them stand out if you, when you've got a sketch in the feature tree, as we have here, either inside a feature or just sat in the feature tree on its own. If you right click on it and go to sketch color in the menu, you can set specific colors for each sketch. So you can see I've got a color palette here, or I've got some pre-selection colors that I can select. And yeah, it just makes keeping track of certain sketches. If one of the sketches is super important in a part, I tend to put it in a bright primary color so that I can see it and get to it easily and quickly. But yeah, that's not specific to patterning. So where were we? We want to create our curve-driven pattern. So again, I'm not pre-clicking on anything now. I'm clicking off in some empty space just over here to make sure I've not accidentally pre-selected something before I create this pattern. So I'm going back to the Features tab, and we know where all the pattern types are kept now. They're in that drop down. And then curve-driven pattern is what I want. In this case, the direction is going to be the curve itself. So the curve is just there. So it's useful that I've put it in that primary color. It's easy to spot. Click on the curve. It's accepted that. And in this particular sort of pattern setup, it now jumps into the features and faces entry box for us. So we don't have to do that manually. So that's useful. And then the feature that we want to pattern is that little triangular extrude. So we can click on any face on the actual feature itself. So click, then we get a preview. What's it doing currently? So at the moment, it's just patterning with a number of pattern members. So you can see we've got 5 pattern members, including the original, and a spacing between each pattern member. So that's how it's generating these 5 that we've got now. And we've already said we want to define this by saying we want equal spacing along the entire curve. So you can see the effect that that just had when I selected it there. equal spacing. So we don't want to tell it what the spacing between each one is. We just want to say use the entire curve that we've given you, and we want to tell you the number of pattern members, which, if I remember rightly, on the old one was 29. So there you go, 29 pattern members. And I think what it's doing in terms of the angle of each one, so here we go, alignment method. You can see it's sort of turning the shape, and I think it's using the curve itself as a reference as to how much to turn the shape. So I think we can turn that off. Where are we? Tangent to curve, align to seed. There you go. So the original feature is known as the seed feature. So that's the one that generates all these copies. So align to seed means that it does not twist the feature as it passes along the curve. So just have a little play with turning that on and off. Tangent to curve and align to seed, and you sort of get the idea of what's going on. So yeah, there's not much more to sort of play with in there, other than, no, we'll not get into the advanced settings for that. We may come back to it later. So you can just click on OK. We've got that pattern set up. If you then feel like you've got the need to hide that sketch now and sort of replicate the behavior of when we create a feature and the sketch gets hidden inside it, you can do. You just find the sketch in the feature manager, click on it, and click on the little eye icon to hide it, and it will disappear out the graphics window. So we're nearly there in terms of these patterns. So let me delete my original curve-driven pattern, which is actually still working. No, I'll leave it there. I'll leave it there. You can see my original curve-driven pattern using those cylindrical extrudes has sort of superimposed itself on top of that triangular one that I've just created. So in that instance, that feature didn't fail. It was happy to create itself as it had done before. And you can see down here, we're seeing that behavior of SolidWorks where when one feature touches or overlaps another, it just unifies them together into a single block of material. So you can see that cylinder and that triangle no longer exist separately. They're just part of a sort of unified cylinder triangle sort of shape. And same over there as well. You can see there's no join between them. They're just part of the same block of material. So I think we've only got one final one to do now. So let's have a look. It's around this side of the block. And so this is the kind of conclusion of our hole wizard tutorial as well. So you can see here what we're looking at there with these holes is a representation of an M12 threaded hole, or a hole that's been machined using a tap. And you can see you get a little sort of graphical representation of what the threads might look like. So you get them sort of shaded in, just using a simple kind of texture to show that there's the thread there. But you also get this little circle round the outside of the hole, which tends to be the method that you use to represent threads on an engineering drawing. You just kind of put a circle or a cylinder of material that's slightly bigger than the drilled hole itself, and that sort of represents that there's a thread within that hole. So we've got a few steps for this one. The pattern that we're using here is, if I can remember rightly, it's the sketch-driven pattern. So the one that we just created was the curve-driven pattern. The sketch-driven pattern, as you can kind of see on the icon, is just driven by a sketch that has points in the sketch. So you can see I've highlighted this sketch in red. You can see if we go into it and edit it, there's just a series of points that I've just dropped at sort of random intervals along this face. Again, for this example, I've not fully defined this sketch. You can see I can just drag these around on the face, but we don't really need to for these particular tutorial examples. So wherever there's a point, the pattern drops a copy of the original feature. So yeah, in that respect, it behaves quite similarly to the hole wizard features that we were creating, except that this one doesn't just apply to a hole, it can be applied to anything. You could use it to pattern an extrude, pattern a cut, whatever you need to do, any feature. So the steps here are that we need to create the sketch that's going to drive all this first. And the reason I say that is that the feature that we're going to eventually pattern really has to be placed in the center point of one of our sketch points. So you can see my original M12 hole, I locked it to be coincident with that point there. And that just keeps everything nice and simple when we create the pattern. You can tell the pattern that there's already a copy there, and you just want identical copies on every one of the other points. So let's create that sketch. So that should be really easy for you to create. I'll suppress all mine that I've created already. The quick way to create a sketch is just to click on a face of the model, and you've got to be careful here because there's two what look like sketch icons there. So just take a moment, be aware of that. There's an edit sketch, which is referring to the sketch that I used to originally create this block. So if I accidentally selected that, it would take me all the way back up to that original extrude, and it would take me back in to edit that sketch. So that's not the one that I want. But that one below it is just create a new sketch on this face. So you can, in the same way that we went into the sketch menu and clicked on sketch up there, you can just shortcut straight to the face itself. And all I'm going to do here, when I'm in the sketch, I'm just going to get the point tool that we've seen in the hole wizard example. So there's the point tool, and get that selected and just drop a few sort of random points on this face. So instances where I've used this before, I've used it where I've been producing machined aluminium plates that have switchgear on them, so that have electrical components on them and circuit breakers and relays and things like that, where they sometimes have a regular spacing, but they sometimes, the spacing between them doesn't really follow any set logic. You just have to be able to drop a copy of a hole wherever you need it. So on a plate such as this, or a block such as this, you probably pick a corner as your reference. So maybe you'd pick this top left corner and you dimension all your hole positions relative to that. So it can be quite a nice tool to use for something such as that, where the pattern members don't necessarily follow a logical, spaced, continuous pattern. You have to have the ability to kind of place them wherever you need them. So that might be a good application for this. You don't need to dimension all these. I'm just giving you the sort of that one method that you might dimension these holes that we're about to put in. So when you've got a few points on there, click on OK. You can exit the sketch like that. The sketch will remain visible because it's not been absorbed by a feature. So you can see there, hopefully, there probably. The sketch is still visible. If you wanted to change the color of the sketch, you could. I don't think we will for this particular one. But we know how to do that now. You just right click on it over there. So we now need to create a hole wizard feature. So hole wizard, we click on the icon, and then this is going to be a tapped hole. So if you search around in hole type for tapped hole, straight tap is what we want. Most of the holes that you're going to encounter are going to be just straight. Certainly in this country, straight metric taps, I would have said. So let's pick straight tap. You can see that representation of the thread itself. You can see that dashed kind of cylinder around the actual drilled hole itself. Let's use, just to be different, let's use ISO as our standard. This is going to be, it's going to be a bottoming tapped hole, which means it's going to be a hole that's got a thread in it. That's what the tapped portion of that means. The fact that it's bottoming means it doesn't pass all the way through the block. So bottoming tapped hole. I think I said M12. So if you want to go down to M12, just plain M12. So in the ISO standard, you can see I've got a few variations of M12. Generally, what you would refer to as standard M12 or coarse, a coarse thread, would just be the one that doesn't have the pitch after it. So I think on M12 it's 0.175 or 1.75, or maybe it's 2 the pitch. I'm not entirely sure. But let's select M12, end condition, blind, and then we'll select the standard depths here. We're not going to change anything about that, but just know that you've got the depth that the drill will go to when it drills the hole. So that is 29.25 in our case. And then you've got the depth that the threading tool or the tap will go to when it cuts the thread. So obviously, when you cut the thread, you don't go any deeper than the depth that the hole's just been drilled. So this is kind of a flash forward to when we get into solid cam and we're programming some of these drilling operations and tapping operations. So yeah, we'll just accept the default there, but know that they're there. This one's for the thread, tap thread depth, and this one is for the drill operation, essentially. And then other options that we might want to set, if you just make sure that you've got with thread call out clicked there, like I've got, and of the 3 options here, you want the middle one. So again, you can see that sort of cosmetic representation of what a thread looks like on an engineering drawing. It's that little dashed portion there. And then our position. So if we click on position, the face that we're placing it on is that face that we've created that dot sketch on. And then all we're going to do is we're going to lock this hole feature to one of the points that we've already sketched. So you can see when I get near that point, it's offering me the coincident relation. So click, and that hole's now been essentially glued to that point. There's a coincident relation between the hole feature and that sketch. So when I've done that, I don't want to place any more holes. So I'm just going to click on OK, which is the green tick. Then I get my hole feature there. You may or may not be seeing this texture that I'm seeing that looks like a thread. We'll probably get into that next week, how to switch that on. I'm just glancing at the time now. Let's just finish this feature, save this block, and then we'll wind up for today. So yeah, we've got our initial feature. Now we want to pattern it using a sketch. So what do? Make sure that we've not inadvertently selected anything. So click in some empty space over here to make sure that you've not left that face selected or left the holes selected. Then pattern type is sketch driven. And what's it asking for? It's asking for a reference sketch. So we know what this is. It's our sketch that's got all the points in them. Then it's asking for a feature. And again, if we zoom in and just click any of the faces on that hole feature, so the cylindrical main face would do there. And then we get our preview. And it looks, if you rotate around a little bit, it looks like it's working. So you can see we have a yellow circle where the hole begins and a yellow circle where the hole ends for each one of those. So that looks good to me. And then we click OK. Yeah, and it's working. So that's that one. So take a save of that, because we may have a little play with those threads. And if you can't see, anyone, can you see that thread texture on your screen that I'm looking at there that looks like a stripy texture? No, I didn't think so. I thought the default setting in SolidWorks had that switched off. Generally, all the default settings are to save your graphics card. If you haven't got a particularly powerful graphics card, they turn most of the features off so that it doesn't slow down too much. But yeah, we'll tackle that either next week or one of the later sessions to switch those settings on. But yeah, make sure you take a save. You should know how to do that. Just click on the little save icon, give it a name, that probably has pattern in the title or something like that. And then at least we've got it as a reference to come into next time. So yeah, I think we'll wind it up. Have a little think on about the project. If you've got any questions, yeah, you can bring them to next week or the weeks after. Yeah, unless anyone's got anything desperate, I think we'll wind it up because I've got another session I've got to jump onto in a second. Yep. Okay then. I'll see everyone next week. Right.